A vector is, can you see that color? Is green okay? We'll change to
Turn off the lights.
Okay. Turn off the lights. No. I think I can't
Yes.
see my note.
No, you look better with the lights off.
It works
I'm
better.
terrible.
You got better?
There you go.
Ooh, but now I can't see my notes.
Now I can see your face.
So, okay. So a vector is a quantity that has, a vector has magnitude and direction. And it's a quantity that has magnitude and direction. And usually we see vectors. Does anyone know where we see vectors? Where do we see vectors? In physics. In what way, Drew? Where do you see them in physics?
Weight, displacement, velocity.
Good. Weight, displacement, velocity. So sometimes they're like forces, right? When you're like pulling, like when you talk about pulling a force on a cable or something like that, that would be the magnitude would be represented by magnitude, and its direction would be represented by a certain vector. But also like movement, like velocity. So if a plane is flying 300 miles an hour at such and such a bearing, that's a vector. That can be represented as a vector. Okay? And vectors are really important in physics and in engineering applications. If any of you going into engineering, you'll take a class probably in the beginning, at least I did, taking mechanical engineering. It's a class called statics. One was called statics and one was called dynamics. And statics is a course where you're dealing with vectors that aren't moving, okay? And then dynamics is one where you're dealing with forces that are moving and stuff like that. And that's like your second year if you go to engineering, so our first year, I think. Okay, but in most classes they'll do that. Okay, vector, magnitude, direction, and another name to represent, and way we represent a vector is with a directed line segment, okay, which means a line segment in a certain direction, okay, and so so we represent vectors kind of, they look like, if I were to draw a vector, they look like a line with an arrow on the end, or a ray, right, and its length is kind of represents the magnitude, and the direction that it's going represents the direction. Okay, so this vector has a certain magnitude and it has a certain direction depending on what the units would be. Okay, so if I have a vector, I'm going to call this vector PQ, and I would represent it like this, PQ, and in the book they put a little one hooked arrow above it, okay? And that would be vector PQ. That's not a B, that's a Q. And P is called the initial point. P is the initial point, where it starts, obviously. And Q is called the initial point. And Q is, in this case, called the terminal point. And the, what else? The magnitude of PQ is represented by its length. So the length represents the magnitude of that vector. And so if you're talking about like miles per hour or something like that, then a vector, a vector that represents 300 miles an hour would be twice as long as a vector that represents 150 miles an hour, and so on. Okay, so that's all there is about vectors. So you can find the magnitude of the vector by just using the distance formula, and this means the magnitude of the vector. So this means magnitude. If you see these two bars around it, it means magnitudes, and it kind of looks like absolute value, which it is kind of like absolute value in that the magnitude is always a positive number, okay? But the two bars on it represent that it's the magnitude of a vector, and the way that you find the magnitude is just by using the distance formula. You guys remember the distance formula? Maybe from geometry, but all it is it's just x1 minus x2 quantity squared plus y1 minus y2 quantity squared. And again, it doesn't matter if you subtract x1 minus x2 because you're going to square it. It doesn't matter which direction you're going because you're going to square it anyway, and you square something, it always becomes what? Positive. So it doesn't matter which you subtract from which when you're finding the magnitude of something. And x1 and y1 represent the x coordinates and the y coordinates of the initial point and the terminal point respectively. So if point P has the coordinates x1 comma y1, then point Q would have the coordinates x2 comma y2. Yeah? And that's how you would find the magnitude of a vector. Okay? What else? When we represent vectors, one way they represent them is with bold-faced, lowercase letters. Bold-faced, lowercase letters. So if I have some vectors, like here's a vector, I might call this vector V. Okay? And then if I have another whoops, I want to draw arrows on the end. If I have another vector going this way, I might call this vector W. Okay? And if I have another vector going this way, I might call this vector U with a lowercase u. Like that. So those are all lowercase. And so when they're talking about vectors, they're bold. I don't know how to make them bold on here. And they're lowercase. And that's one way they shorthand of representing vectors. Can I move on? Are we good? Okay. Vectors are equivalent if they have the same magnitude and direction. So show that PQ and RS okay. So the first thing that you got to do is have a point for P. So P is 0, 0, and Q is 3, 2, and R is 1, 2, and S is 4, 4. So what should I do first to do this? It's really dark in here. So is that okay? It's really dark in here? Okay. So find the magnitude of PQ. So the magnitude of PQ, 2 bars, is equal to the square root of 0 minus 3 squared. You could go the other direction too, it doesn't matter. Okay, plus 0 minus 2 squared. Yep. Which gives you square root of 9 plus 4 equals the square root of 13. And then I have the magnitude of vector RS is equal to the square root of, let's go this way since I don't won't get negative numbers. 4 minus 1 is 4 minus 1 squared plus 4 minus 2 squared. Is that the same? Yeah, so I get the square root of 9 plus 4, which is the square root of 13. But I'm not done yet, because what else do I have to show?
9 plus
9 plus 3, oh, I meant 9 plus 4, sorry. 9 plus 4 is 3. So now I have to show that they're going in the same direction. How do I find out if they're going in the same direction?
you draw it.
Yeah, you could draw it, but better way is to find the slope. Okay, right? If they both have the same slope, then they're both going in the same direction, right? So hopefully you guys remember the slope formula. So I'm just going to go y2 minus y1. So the slope, I'll do like this, the slope of PQ, okay, with a little bar over it, is equal to y2 minus y1, 2 over x2 minus x1, which is 2/3. The slope of RS is equal to 4 minus 2, which is also 2, over 4 minus 1, which is 3. And so do they both have the same slope? So they're both going in the same direction. They both have the same magnitude. Hello? Yes? Say yes. Yes. Okay, that's it. Okay, so if I were going to graph this, graph to show their equivalent, okay, I'll do a different color here. So this vector from 0, so let me just put some points on here. 1, 2, 3, 4, 1, 2, 3, 4. So this vector from 0, 0 to 3, 2, 3, 2 might look like this, right? So there's PQ, and RS goes from 1, 2 to 4, 4. 1, 2, up to 4, 4. So it looks like that. You see how those two things look about the same length and in the same direction, and so they're called the equivalent vectors. Okay. Standard position.
Wait, Mr. Leader,
What?
is the 13 still supposed to be under the square root, or what happened to the
Yes, I'm stupid. Yes, the square. It should be under the square root. Sorry. Thank you.
So why did we find that to just go and find the slope?
Because not only do you have to show that the slope shows that they're going in the same direction, the magnitude shows that they're the same length, right?
Okay.
So I could have the same slope, but they could have different magnitudes. Yes, Julian.
How did you find the slope?
Y2, right? So I use the formula y2 minus y1 over x2 minus x1. You remember that, right?
Yeah.
So 2 minus 0 over 3 minus 0. For that one, for PQ.
Okay.
And 4 minus 2 and 4 minus 1 over 4 minus 1.
Okay.
Easy?
Yeah.
Okay. Okay, what else? Find slope and magnitude. Standard position. There's lots of notes. I don't know what to tell you. Okay? Standard position. What's that noise outside? Or is that someone snoring? It's windy? Standard position. Initial point. Sorry, I gotta pause. We're gonna pause. I gotta find out what. Standard position means that the initial point is at the origin. Okay, if you were graphing it. So, so this vector would be said. I don't want to put arrows on. Let's put arrows on both. Let's do undo that. Let's go here. Let's put arrows in. So standard position, and this form, which you're going to see, 3v equals 3 comma 2. This is called component form of a vector. Component component form where this is like the x component and this is the y component. And they have little angle brackets on the end. So the component form, if I want to write this one in standard position, I would go over 1, 2, 3, and up 2, 1, 2. And the component form of that vector would look like this. I mean, not the component form of that vector in standard position. So the initial point is the origin. So if you just see this, I mean, starting at 0, 0, I would go over 3 and up 2. Okay? And component form looks like this, but more generally, it looks like V equals V1, comma V2, where this is called the horizontal component, and this is the vertical component. Yeah? Horizontal, vertical component.
So,
With P1 prefactor 712 given by. Yes?
So in the book, when it just says, do the component form, you start at 0, 0, and you add that whatever is in the V? Is that what it said?
No, that's if they say put it in standard position. Okay? But, so, for example, let me say, component form initial point P1, T down term the point Q1. Magnitude I talked about. So let me just write this. Well, I'm going to use my line paper. Component form. I shouldn't use the lines. I can't stand lines. Of a vector with initial point P is P1, comma P2, and terminal point Q, which they say is little q1, comma little q2. These should be little or q's, doesn't matter. Okay, is equal to, in brackets, q1 minus p1, comma, q2 minus p2, which is equal to v1, comma v2. Okay, so all this says is to find the. So if you have some vector that goes from point P to point Q, you subtract this minus this, and that will give you the horizontal component, and you subtract Q, the y component of the, or the y coordinate of the terminal point minus the y coordinate initial point, and you'll get the horizontal component. Understand that? We'll do an example in a minute. So, do I have an example? Yeah, I do in a minute. So, and then we talked about the magnitude of V of any vector is equal to the square root of V1 squared plus V2 squared, which is this squared minus this squared. So really it's just the distance formula. And the other thing, if, we'll talk more about this tomorrow, but if V, the magnitude of V is equal to 1, then it's called a unit vector. And that's important to know what a unit vector is. And a unit vector is a vector with a magnitude of 1. So if I were graphing, just real quick, if I were graphing and I have a vector here and it's going up here, and its length is 1, then that's a unit vector. Yes, Julian?
So is the component form just like the slope?
Not really. It's just breaking it. So,
I mean, it's
well, it's the x and the y part, right? So if I have some vector, let me just draw a picture, okay? So if I have some vector, let's make a different color vector. Purple. Here's a vector, and it's going like this. Yes?
Yeah.
I could break it into 2 components. One being a horizontal component, right? And
So
one
rise over run.
and one being a vertical component.
So rise over run.
Yeah, it's rise over run, but just this. But it's also the length of the rise over the run, right? It's not just.
Well, I mean, so if it has a direction and then it's okay.
Yeah, it could have its same direction, but be a different length, right?
Okay. Yeah.
So like this vector is not the same as a vector going in the same direction, right?
So like a slope of 6/4 is not the same, or a
Exactly.
component of 6/4
Right.
is not the same. As
Yeah, that's the main difference. So if I have a little vector going this way, that lies on top of that vector, they are equivalent, they are the same direction, but they're not the same magnitude,
Yeah.
right? Okay. So that's a good question. Yeah, so it's not just the slope, it's also the magnitude of its components, right? Okay. So that's, and and this thing, if they have this thing like this, if the magnitude is equal to 0, that's just called the 0 vector. And that's a vector with no magnitude and no direction. Okay? So it's bad to have no direction, right? But it's better to have a magnitude of 1, because then you could be like that famous pop band. One Direction. Made a joke. That's a new one. Okay. Okay. Sorry. One. It's not that funny. Form and magnitude of PQ if P goes from -3, 2, and Q is at 5, 3. 5, -3. Could you do that? That's it. So what's the component form of the vector? Yep, -3 minus, no, -3 minus 2, right? Minus 2. So, oops, I messed up. It's not -3 minus 2. You do the x's first, right? 5 minus -3, comma, -3 minus 2, which gives you 8, comma, -5, okay? How do I find the magnitude of that? The magnitude, all you have to do is square this, right? V1 squared minus V2 squared, or plus V2 squared. So it's 8 squared plus -5. When you square a negative, it becomes positive, which is the square root of 64 plus 25, which gives you the square root of 89, which is whatever it is. Okay, 9 point something. Okay? Yeah?
So if you have the component form, you don't.
This is component form right here.
So you can just plug it into the.
Yep. That's what's nice about once it's in component form, all you have to do is take this squared plus minus this
You
squared.
don't,
'Cause
okay.
Yeah, because you've already, basically here, you've already done
The-
x1 minus x2, right? That's what you're
So
doing
why do
here.
you have to do the component
Okay,
form?
Drew and,
Yeah, what's the point
What's the
of
point of doing the component form? Why didn't you just plug it into the, like, under the square root? You're just done.
because when you're adding and subtracting vectors, component form is a lot smoother, which you'll see in a second, okay? So, so scalar, vector, so the next thing we're talking about is vector operations, okay? So, whoops, oh well, it's okay to. Vector operations that we're going to talk about today, okay? You can add and subtract. Add and subtract. And you can multiply by a scalar. A scalar is just a number, like a raw number, like k equals 5 or something like that. Okay? So first we'll talk about multiplying by a scalar. So k times some vector v, okay, where v, k multiplied by v, this is a scalar and this is a vector. And it stretches it. Stretches, shrinks, or reverses if it's negative. Reverses if negative. Okay? So say if some vector v equals 2 comma negative 3. And I want 2 times the vector v. What's that going to look like?
4,
Yep.
6.
It's just 4, negative 6. Very good. So if vector v is going, I hate this thing that it has. So 2, negative 3, let's just say that one goes 2 over 2 down 3. So something like that. So if I do over 4 down 6, it's just going to take that same vector and it's going to stretch it down in this direction. I didn't make them exactly on top of it, okay? But you get the idea, right? Over 4 down 6. So that's a scalar. This is a scalar. If I multiplied it by negative 2, what do you think that's going to do? It's going to make it go the opposite direction. Okay, so if I multiply by negative 2, you would get a vector going this way. Okay, you would get a vector going this way that's twice as big, but it'd be going in the opposite direction. Okay, if I multiply by a number less than 1, what's it going to do? Squish it, right? And so on. So that's scalar multiplication. And then, and the way the rule used is k times v is equal to the vector k v1 comma k v2. In other words, you just multiply the horizontal component and you multiply the vertical component. I'm not going to do an example because I want to get to addition. Okay? I got 5 minutes. I'm sorry it's a short period. Okay? Addition and subtraction. Vectors. Add tip to tail. Okay? So just kind of graphically, say I have a vector that looks like this, and I'm going to call this vector v. And then I have another vector that looks like this, shorter, and I'm going to call this vector u. Okay? Okay? And I want v plus tail. That's sorry. Okay. V plus u. the way I would do it is I just take this one and add it to this one. So I'm just going to, so if I wanted to do v plus u, I can do this graphically. Look at this. I can just grab this guy and move him over here. And the resultant vector, this thing is called the resultant vector. And this is called, that's called the resultant. Okay? So that's what v plus u would look like. Okay? And I could have also gone another way. I could have done this. It doesn't matter what order I go in. So I could have gone u plus v and got to the same spot. Okay? As long as I'm adding the tip of this one, there should be arrows on the end. Where'd the arrows go? Maybe it's too short to ever. But I could have gone u plus v this way, and it should make a parallelogram. Okay? So when you're adding vectors, you add the tip of one to the tail of the next one. And it doesn't matter which one you do first. Okay? And that's real important when you're doing like airplanes, flying 300 miles an hour in this direction. The wind is blowing 30 miles an hour in this direction. Which way are you actually going? Yes, sir.
Which side is the tip and which side is the tail?
This is the tip. This is the tip, and this is the tail. The end is the tail,
Okay.
and the tip is the point, right? But it doesn't matter which tail, tip and tail you do. No? Yeah? So, and then algebraically, the way you add vectors, that's why you like component form. If you have one vector, so the way you add them is just by adding them up. So if v equals -2, you add up their components. So if v equals -2, 5, and u equals 3, 4, and they say find v plus u, I would just go, I add up their components. So it's -2 plus 3, which gives you 1, and 5 plus 4, which gives you 9. And so that's the resultant vector of adding this plus this. So for example, if I were going to show you this graphically, right? If I were going to show you this graphically, not time to go yet, almost time to go. So -2, 5 would be back 2, up 5. So this one might be something like this, right? From that point, I'm going to go over 3 and up 4. So maybe somewhere like that, right? The result of that would be the same as going over 1 and up 9. Okay? So this here would be the result. Here's u, here's v, and I add those two together and I get there that way. Okay? How would I do u minus v or v minus u? Subtract. And graphically that would look like u minus v would be going that direction, right? And if I want to do 2v minus u, I multiply this one by 2 and subtract that. Easy. Okay? So that's pretty easy stuff, right? Okay? And I don't think your homework is too brutal. It'll go fast. But make sure you're doing the graphical, where is it? Graphs as well as algebraically. Chapter 6, it's on my website. There it is. Is this it? There it is.